Okay, so Unit 10, the fundamental theorem of calculus. This is the the basic thing about integration. Okay, in the last unit, Unit 9, we saw how to compute from a given function its primitive. That is the function that when you differentiate it, you get the function that you were given at the beginning, right? The fundamental theorem of calculus actually relates those primitives to the calculation of integrals. Okay, so what are integrals? We're from the early Greeks, from Archimedes and early on. Well, there was in the ancient Greece, there was a big focus in geometry, right, in computing geometric variables, right, and solving geometric problems. And so one of the problems was to compute, for instance, areas and volumes of forms, right? So if you have like a square, it's easy to compute its area, right? We know the formulas. If you have a triangle, you know how to compute those. And the Greeks actually developed quite a lot of methods to find the area of any polygonal form, right? The problem became what happens when you have forms with curved surfaces, right? And for our purposes, that means what happens if you have a function like this, and if you want to compute the area between this function and the x-axis, right, between 2 points A and B, what's the value of this area? Well, that's where the integration comes in. Okay, the integration, an integral is to compute the area under the curve of this curvature. Okay, and so the basic method that the Greeks developed and that was refined during the years is that, well, we can actually approximate this area by dividing this interval into pieces, and then in each piece of this interval, right, we can approximate this area by approximating the area of the function here, right? Or sorry, the height of the function. Okay, typically with rectangles. Okay, and then if we get to very very narrow intervals here, then the area that we get by summing the area of these rectangles will approximate very well the area under the curve, right? That's this idea. So for instance, suppose we want to compute the area behind the function x squared, right, between 0 and a point A. So what's this area? Okay, so the idea is, well, we can divide this let's see, this interval 0a in n different points, right? And so each one of them has width of a divided by n, right? So you have this interval that starts at 0, right? Or let's see, the points that divide the interval are 0, a n, then you have 2a_n, 3a_n, and so on, right? Until you get n minus 1 over n times a and a, right? Those are the points. So we want to get an approximation of the function in this interval, and we're going to see, well, this is in this interval between 0 and a n, we're going to get the highest value of the function, right? Which is this is x squared, right? So the function of x at the point, rightmost point, k a n, right? So k goes from 0 to n is k squared a squared divided by n squared, right? Now the sum, the area of each one of these rectangles, the kth rectangle, right? The area k is just this function times the height, right? So it's times the width, right? N squared, and then you have a divided by n, right? This is the width of each of these intervals, right? So you have a cubed divided by n cubed times k squared, right? And now the total area is the sum from k equals 1 to n of this value, right? A cube n cube, sorry, this is n cube to k squared, right? And so a cube and n cube go out of the sum, and you have the sum from k equals 1 to n of k squared. And this is the sum of the first the squares of the first n natural numbers, and we've seen this before in unit 1. This is n times n plus 1 times 2n plus 1 divided by 6, right? So this sum is equal to a cube divided by 6, and then this is equal to n times n plus 1 times 2n plus 1 divided by n cubed, right? Now the idea that we were saying is that, let's call this a n, right? This depends on the number of intervals. Now the actual area, if this procedure works, is what happens when the number of intervals that we take goes to infinity, the limit when it goes to infinity of this area a sub n, right? And so this limit is a cubed divided by 6, the limit of n plus 1, 2n plus 1 divided by n cubed, right? Let me erase this. Okay. This limit, if you see, this is n times n plus 1, this is goes like n squared, and this is like 2n cubed divided by n cubed. This limit is 2. So this area is a cubed divided by 3. Okay, that's the area between 0 and a of below the area the function x squared. Okay, so that's the idea behind this method. Okay, this integration, right? How to compute areas below curved functions. Okay, this is the approximation. So this is kind of a very intuitive idea. Can we put some rigor behind it? This is not proven that it's going to work every time, right? So this is what Riemann, he was a German mathematician in the 19th century. So he came up with this idea. Okay, suppose that we want to integrate a function in an interval a, b, right? So we want to define a partition, what we call a partition of this interval. So it's a set of points x0, x1, x2, blah blah blah, xn, right? Where x0 is equal to a and xn is equal to b, and x1 up to xn are points between those, right? So just like those that we chose, right? So this is a, this is b, and then we have x1, x2, x3. They don't need to be like equally spaced, right? They can have any distance between them. Now in every of this, if we have a function that is bounded in AB, right? So f is bounded, then we have that it will have a maximum and a minimum inside each of these intervals, right? So we have the maximum, the minimum at the interval I, which we call this is the infimum. It doesn't have to have a minimum actually, between x minus 1 and I minus 1 and xi. So in this, for all the values of x in this interval between these 2 points, for instance 1 and 2, we have the value of the function there, right? So the minimum in the first interval is the infimum between x0 and x1, right? So this is the first interval, right? So this is the minimum and this is the maximum, right? The supremum of the function in this interval between xi minus 1 and xi, right? Okay, so we have the function is going to be between these two values, right? So suppose that the area, let me try to draw this, right? So we have this, right? And suppose we have these 2 points, xi minus 1 and xi, right? So this is this, right? In this interval, right, the infimum on this is mi, and this is going to be capital Mi, right? So the the area here of this rectangle, right? We choose this rectangle as we did before. The area of this rectangle is going to be mi times xi minus xi minus 1, right? And the area of this rectangle, which includes all of this, right, is capital Mi times xi minus xi minus 1, right? So now we can sum the areas, like this is the big area, what we call the upper area, and the lower sum, right? So the upper sum of f with this partition is defined as the sum from I equals 1 to n of mi times xi minus xi minus 1. So the sum of the large rectangles, right? And the lower sum is the same, but with the infimum, right? The small rectangles, right? So what yeah, I forgot to say is that this method, obviously, if you think about it, if you have a function that goes below the x-axis, this will count as positive area, and this will count as negative area. Okay, you can see that because we're considering the value, the actual value of the function, okay, and not only the absolute value. Okay, so this is, remember, this is called the upper sum, and this is called the lower sum. Okay, so it's obvious that let me erase some of this. Okay, it's obvious that the lower sum is always going to be smaller than the smaller equal than the upper sum, right? So what Riemann said is, like, we can refine a partition, okay, by adding points to it. So for instance, if we have another partition Q in which we have x0, x1, x2, and then let's call it xn plus 1, for instance, and then we have x3, x4, xn plus 2, and so on until we get b again, right, which is xn origin. So we insert new points in here, right? So partition P, right, is included in this Q, right? So this is a more refined, which we call a refined. Q is a refinement of P, right? Now, if you think about it for a second, you realize that the lower sum corresponding to this new refined partition is going to be greater than the lower sum for the other coarse partition, okay? Because if for instance, if you have this function like this, right, and we have the original partition, let's call it x1 and x, in this case, for instance, x2 and x3, right? The lower sum in the original one is this, right? But now in the new one, suppose we have let's suppose we have xn plus 1 is here, right? Right, the new lower partition, in this case it will be this, right, plus this. So this area is going to be greater, okay? At least it's going to be equal, but in many cases it's going to be greater, right? If you have more points, then the minimal value in some of the new intervals will be greater than the minimal value before. And similarly, it will be the case that this new and the upper sum is going to be smaller than the upper sum for the other partition, right? So this is P, right? And again, because the maximal value in this new partition will have smaller values in some new intervals, right? So then we can say, suppose, well, yeah, and of course, if we have any two partitions, P1 and P2, then we can bind them together or join them together, like say Q is the union of P1 and P2, and now Q is both a refinement of both, and so we have that the sum, the lower sum of P1 is going to be smaller than the lower sum of q, right? Because this is a refinement, and we have that this is going to be smaller than the sum u, right? The upper sum at the same partition, because that's what by definition, and then this is going to be smaller than the original sum for p2, right, for instance. So we're going to have that the lower sum is always going to be smaller than the upper sum irrespective of the partition, right? So it doesn't matter how you partition this interval, you're always going to have that the lower sum is going to be smaller than the upper sum. And this is summarized like this: the supremum, okay, of the partitions, sorry, the sum of the lower sum for all partitions, it's going to be smaller or equal than the infimum of the upper sum for all partitions. Okay, this is what this implies, right? So for any partition that we make, the greatest lower sum among all of them is going to be smaller than the smallest upper sum that we, smaller equal, okay, than the smallest upper sum that we choose. Okay, and so this led Riemann to the following definition, which is the integral. Okay, and he says a function f that is bounded in closed AB is integrable in this interval if the supremum of L, of the lower sum for all partitions, is equal to the infimum of U between all partitions. Okay, so that means that if we get, you know, we get the partition for which we can make the lower sum as great as we can, right? That's the supremum, has to be equal to the infimum of the upper sums. Okay, that means that this strategy that we have making with the rectangles will coincide. You know, both the upper sum and the lower sum will merge together in the same value, and that value is what we call the integral, right? This integral between a and b of this function f. Okay. Well, we typically, so that was Riemann's notation. Typically use this notation, right? Fx dx, which was Leibniz notation. Okay, so the idea that Leibniz has is that we're summing. So this symbol for the integral is an s, right? This an s for sum. Okay, so we're summing the values of f, right? The areas of rectangles with height f, right? F, and width dx. Okay, so dx, the idea is that it is very, very small x. Okay, so yeah, not all bounded functions are integrable. For instance, you know, typical example of non-integral function is that if we have one, the function that is 1 when x is a rational number, and 0 when x is not rational, well, it's not going to be integrable because the supremum of the lower sum, okay, sorry, the lower sum for every partition, right? It doesn't matter what partition we choose, the lower value of the function is always going to be 0, because in all intervals there's always going to be at least one irrational number, and the upper sum, it's always going to be 1, okay, because in all intervals there's always at least one rational number. So this is true for all partitions. Okay, so the supremum of L is going to be 0, the infimum of U is going to be 1, and so it's not equal. Okay, these two things are not equal. Okay, one example of an integrable but weird function is, for instance, this f is the function 1 when x is 1/2 and 0 when x is different from 1/2. Okay, and in this case what we have is that the lower sum obviously for all partitions is going to be 0, right? And the upper sum is going to be, let's say, delta x, okay, where delta x is the value. So this is 1/2, this is 1, right, because that's the value of the function here. Delta x is the width of this interval, right, containing 1/2. Okay, but then we can refine this partition, right, u, by making this, you know, narrower and narrower and narrower until the width around 1/2, you know, the limit of that goes to 0. Okay, so we can take this and go to 0. So the limit, the supremum of L, which is 0, coincides with the infimum of u, which is 0. And so the integral of this function between, for instance, 0 and 1 is 0. Okay. Okay. So let's see. From our, you know, heuristic construction that we were using at the beginning, we can say we can derive this theorem that is very important in many applications. So the bounded function f is integrable in AB if and only if there exists a sequence of partitions Pn such that the limit when n goes to infinity of L is equal to the limit when u goes to when n goes to infinity of u with respect to Pn. Okay, so this is the idea that we can take this regular partition with you know, between a and b, with the width of this interval is b minus a over n, and we can take you know, the limit when n goes to infinity. This partition is going to be refined and refined and refined more and more and more, and the limit of the lower sum will get to the supremum, while the limit of the upper sum will get to the infimum. Okay, so if both things are, so this is going to be equal to the supremum of with respect to all partitions of L, and this is going to be equal to the infimum with respect to all partitions of U, right? So if those things are the same, this is going to be integrable. Okay, and then with that, you can, I leave you to do it at home, to transform what we have done. Well, example 10.1 is the integral of x squared between 0 and a, right? This function that we had integrated before, right? So to do it using this result. Okay. We're not going to get into which functions are integrable and which are not, okay? Because yeah, that's a long story, right? But for practical purposes, there are a couple of results that are important. The first one is if f is continuous, then it's integrable, okay, in AB, okay? The idea is, of course, that you know, given a partition, right, you're gonna have the lower sum is gonna have the sum from, you know, k equals 1 to n of the minimum at k, right, between x k minus xk minus 1, and the upper sum is the sum between k equals 1 and n of the maximum, right, xk minus xk minus 1. So the how to say this, that the idea behind Riemann's definition is that we have to find, for instance, that let's use a partition Pn, right? And so the limit when n goes to infinity of the difference between this and the lower sum, right? This has to be 0 if f is integrable, right? This is the idea behind the definition. But what's this? Well, this is the sum from k equals 1 to n of nk minus small nk times this, right? xk minus xk minus 1. Well, the idea here for, let me say this, for a continuous function is that the difference between the maximum and the minimum, okay, can be as small as we want, okay? So as we reduce or narrow the intervals, right, this distance between x and x minus 1, xk and xk minus 1, the distance between mk and mk capital MK and small mk will be getting smaller and smaller and smaller. Okay, and that means that in the limit this will go to 0, this difference. Okay, that's because that property of the continuous functions. Okay, similar result is that if f is monotonic in AB, then it's integrable in AB. So for instance, if we have a partition Pn, right, if f is monotonic, let's suppose it's increasing, right? So the sum from k equals 1 to n of the minimum, right, times xk minus 1, and then uf Pn is the sum of k equals 1 to n capital A, right? Right, mi in a monotonically increasing function, right? We had seen before, this is not monotonic, so a monotonic increasing function in an interval mi, it's going to be f at the well, xk in this case, sorry, it's k, this is k. And this is going to be f at the leftmost value, xk minus 1, and the maximum is going to be f at xk, right? So this is f at xk minus 1, this is f at xk, right? So if we compute, let's see, the limit, or, well, and so this is again, xk minus 1 is b minus a over n, okay? We know that. So if we compute the limit, right, of the limit when n goes to infinity of ufpn minus l fpn, this is going to be the limit when n goes to infinity of the sum, and so b minus a goes away, right? So b minus a and over n, right? Because this doesn't depend on the index, right? So then we have mk minus nk, which is f at xk minus f at xk minus 1, and this is a telescoping sum. So this, if you do it, you get this is f at xn, which is f at b, minus f at x 0, which is, this is b, right, and this is a. So this is f at b minus f at a. Okay, so let me rewrite all of this as f at b minus f at a. But now f is bounded, right? So fb minus fa is a finite quantity. B minus a is also finite, so you have this goes out of the limit. The limit when 1 over n goes, so when n goes to infinity, sorry, of 1 over n is 0. Okay, this limit is 0. Okay, so that's the result for monotonic functions. Okay, now so there's some basic properties to the integrals, right? So if f and g are two integral functions in closed AB, then we have that the sum or the linear combination, sorry, the integral of the linear combination of f and g, right, is the linear combination of the integrals of f and g in that interval. Okay, and this is easy to prove. The idea is that if you go to the partitions, right, in that partition, in every partition, in every interval in the partition, the value of the rectangle, if you want, is going to be alpha f plus beta g, and you can separate that. Then the sum of that can separate the sum for f and the sum for g. Okay. Now, if f is greater, so if g is greater than f for all points in AB, then this integral will be greater, and then if f is integrable, then the absolute value of f is integrable. And this is a very interesting inequality. The absolute value of the integral is going to be smaller or equal than the absolute value, sorry, the integral of the absolute value of f. Okay, so as consequences, obviously, because if g is greater than 0, then this implies that the integral between a and b of of g is going to be greater or equal than 0, obviously. And then from this we can also say that if we take m is the supremum of f in this interval, right, in AB, and then smaller m is the infimum of f in AB, right? Then if we take a function that's constant in this interval, like m only takes m and m, from this second property we get that the integral of f between a and b is smaller than or equal than m times b minus a, and this is going to be greater than the minimal value. Okay, now we also have that this property of interval additivity. So given that a is smaller than b, that's smaller than c, function f is going to be integrable in a, in this closed AC, if and only if it is integrable in AB and BC. Okay, so that means that if it's integrable in both of them, it will be integrable in this. If it's integrable in this way, you can separate the integral. Okay, and this, the value of the integral will be the sum of the two integrals. Okay, now we can separate this. We can say that the value of the integral from a to b is the value of the integral from a to c minus the integral from b to c. Okay, if you think about this in terms of areas, this is kind of very intuitive, right? So and we can't how to say this, if you think about this, you can write this rule like this: ACF plus CB, right? And then you will have that the rule of additivity is maintained even if this condition is not fulfilled, right? So C is any point, right? So that is true if we say that this is true, right? This, the interval between B and C, how to say this? The integral between C and B is going to be equal to minus the integral between B and C. And this is important, this is a definition, okay? We have to define this integral like that because this is the integral as we have seen it so far is defined in an interval, right? Close BC, but the interval close CB doesn't exist, right? Because C is greater than B, right? So you can't use the definitions that we have seen so far about the integral, right? So we have to define whenever we have the integral of f in and the boundaries of the integral are points that are not, so this one is smaller than this, then this means that this is minus this integral. Okay. Okay, for the last part of the video, we're going to talk about Riemann's sums, which are given by this formula. Okay, so given a function f that is bounded in this interval, right, AB, as we have seen so far, then we can write for any partition P, we can write this sum, right? This is the value of f at Ci, where Ci is any point between the extrema of the interval, right, times xi minus xi minus 1, right? So whenever you choose a value C, you are going to give like Riemann sum. Okay, for this definition, it's clear that there's this condition. Any Riemann sum is going to be smaller than the upper sum, and it's going to be greater than the lower sum. Okay, for corresponding to that partition. Okay, so if f is integrable, right? So then we have that. Let's see, if f is integrable, then we have seen that the limit when n goes to infinity of the difference between UFPN minus LFPN with a sequence of partitions that get finer and finer and finer is going to be 0, right? But now using the sandwich theorem, right, this implies that the limit of, so that means that this difference is 0 and that both partitions go to the integral, right? So that using the sandwich theorem implies that the limit if you choose any sequence of partitions that gets finer and finer so that this thing goes to 0, the limit of s with respect to that partition is going to be the integral. Okay, and that thing is going to be useful for calculating some limits. So for instance, suppose we have the limit when n goes to infinity of the sum from k equals 1 to the n of 1 over n plus k. Right, so this is not a series because the sum is defined in terms of n. The general term also depends on n, right? But we can rewrite this as this. This is the limit when n goes to infinity of the sum from k equals 1 to n of 1 over n, and then we have 1 over 1 plus k over n, right? So now 1 over n can go outside, or if you want, let's see, wait a minute. So this 1 over n is, you can think of the width of the interval, right? Of the interval of the partition. The intervals in the partition, right? And this is f at the interval k over n, right? So this is the function f is 1 over 1 plus x, right? So this is exactly this. This is f at some point in the interval, right? This is the difference between the interval. This is the sum, right? And we know that the limit of this is going to be the integral of this function between a and b, right? Now, in this case, a, if you see here, when k equals 1, this is from 0 to 1. Okay, the interval is from 0 to 1. Okay, and so we just need to compute that integral. Okay, the primitive of this, the integral of this we'll see later on how to compute this, but this has to do with the primitive of this. Okay, another example. We have the limit when n goes to infinity of the product of k equals 1 to the n of 1 plus k over n to the 1 over n. Okay, in order to get this, we call this is L, we compute the logarithm of L, and so this is the logarithm of all of this, which is the limit when n goes to infinity of the logarithm of this. So you have 1 over n, the logarithm of the product, which is equal to the sum from k equals 1 to n of the logarithm of 1 plus k over n. And just like before, 1 over n is this thing, and this is this value, right? The value of the function f, which in this case is the logarithm of 1 plus x at the right end of the interval, right? So the limit of this is going to be the integral between 0 and 1 of the logarithm of 1 plus x. Okay, dx, right?